Okay, I guess it's time to start. Well, thanks everyone for coming. This is new for me. I've never done a two-sided presentation, so yeah, I will try to also forward the audience on the other side, but mostly I'll be looking at this side, if it's fine for you. Okay, my name is Gonzalo. I'm assistant professor here at Skoltech. Well, today's talk is maybe a little out of the standard of what you've seen during this week, right, on machine learning, but still robotics, I think it's a relevant topic, right, to machine learning, especially these days. So, well, first let's talk a little about Skoltech. Did any of you heard about Skoltech before coming here? Okay, we have some people. Other? Okay, great. So basically it's a new university. The idea is that we do both applied and basic research, right? And we also want to try in the next generation of scientists, innovators, and, well, etc. Right, so basically we are trying to bridge this gap between the industry needs, right? So nowadays this is very competitive area, right? It's not just locally, but we are competing, industry is competing like internationally, and well, research also has to be connected to this. So new campus, it's this thing. It's still not fully operative, so for classes, it's awesome, right? All these new spaces. Some departments are already here, but not all of us move. So I hope that will be soon, right? So it's very exciting, but we'll see. Anyway, I hope you have enjoyed this stay during these days right here. So you have cool spaces, hopefully. And well, I'm really looking, I'm still on another building. So that's what I'm saying this. Okay, so more specifically, about our group, right? So we are inside CDISE. What is CDISE? So inside the university, there are like several groups. One of them is dedicated to computational data-intensive science and engineering, right? So currently, as I said, since we are a new university, everything is growing, right? The number of faculty, the number of researchers, PhDs, masters, etc., right? We also have like, or offer two master tracks. One of them is purely on computational science, and the other is more related to engineering and data science. Okay, so what kind of research do we do here? Mostly, as you have guessed, so it's machine learning, right? We have a lot of professors who are, whose groups are dedicated to machine learning, right? Deep learning, data mining. Also, there's a big chunk of groups dedicated to modeling. And also, there's robotics, right, with us, I guess, right? So that's the next point, right? So the mobile robotics lab, right? So I'm responsible for this lab. The same as the university, this is growing, right? So now we have some students and some masters, but what is the idea, right? So robotics is very wide. I think in general, people have like different conceptions of what robotics is. So depends on who you ask, right? I'm not going to say that my definition is right, but for me robotics is more related to the artificial intelligence part, right? So hardware is important, but I think we have achieved a level that it's very good, right? And what is lacking behind is actually the soft part, right? So in particular, the objective of our lab will be to deploy robots either in outdoors, indoors, any environment, right? And just do decisions intelligently in the world, right? So if you think about this, this is just the embodiment of AI into some devices. Are we interested in hardware? Well, yes, but we mainly do research just on the algorithmic part. Okay, so which are our research topics? Robot perception, right? What is this? So it's all the perception, especially dedicated to robotics. In this case, this includes localization and mapping, SLAM, and we're also interested in people detection and tracking. There's a course, by the way, in our program which is dedicated to this. Nowadays, localizing your devices and doing mapping is important, right? Part of this pipeline requires also computer vision or computer perception, right? Just to pre-process all this information into something meaningful that then we can convert into maps, right? And what is a map? Well, that will be another talk. Second topic is on robot navigation, right? So here we're interested in path planning. So very shortly, what is path planning? We have a state or a robot that is at initial state, and we want to move or transform this state A into state B, right? So how to do that? Well, it can be trivial for some states, like you move from this position to this, there's nothing in between, so that's easy. What happens when we have highly dimensional systems where things are dynamic, we have uncertainty, right? So this is a little current research topic. And well, more in particular, as I just mentioned now, it's dynamic environment, so this is a particular problem in path planning. The problem here is that our obstacles, or let's call them part of our state variables, just change over time, and it's hard to predict these changes. Okay, so briefly, what is the outline of this presentation? Well, first, I'm gonna introduce a little this problem, right? So maybe this goes a little out of what you've been talking all this week, or a little out of machine learning, but you will see the reason later. Right, so this problem, I will talk about some of the solutions that we found. Basically, they are based on some models, right? They might be better or worse, these models, but they work. I will talk also about the limitations here, and basically it's this, using model-based prediction and planning techniques. Then later, well, I will talk about some approaches that are actually inspired by machine learning. I will also discuss how to include machine learning on all the talk, right? But basically, there's like very interesting tools and very powerful tools developed like during the last years for the other communities, right? That I think we could also use them in robotics, right? And just to get like much better solutions. So I will also talk about this. And then lately, I will talk about the current limitations on and opportunities, right, for machine learning in robotics, right? So it's not exactly a straightforward application of all the algorithms that are there, but there are like some peculiarities, right? And these actually make the difference. Okay, so let's talk about the problem, right? What is a dynamic environment? So for instance, take a look at this video, right? This is a crossing in Tokyo, right? Almost thousands of people are just crossing at the same time. So this is highly dynamic system, if you want to think about this as such, right? And what is happening is that some agents are from in one side, the others are in the other side, they have limited time, and they need to cross, right? And it's not just that. This is not just a problem of moving from one point to the other, right, of these multiple agents, but at the same time, they don't have to collide, right? So collide is very impolite. So the problem is really challenging, right? My talk, this is a spoiler, it's not gonna finish with thousands of robots moving like this. I wish we were there, but this is still a little far, right? But just to put a milestone of what we should be looking at is this kind of capabilities, right? So thousands of agents moving. We still can do other tasks, like some of these maybe are looking at their phones and still not colliding, but this is pretty impressive, right? What human beings are capable of, right? So this is something that we should be looking at. Okay, now let's take a look at some state-of-the-art approaches, right? So this is the dynamic window approach, a very famous and widely used planning technique, right? And this is what happens when we don't give enough time, or let's say that the prediction time is not enough just to calculate a valid path. So we simply have an agent that comes in while the plan was not, when initially on the plan it was not included, right? So with this technique, with this kind of technique, which is applied to static environments, you cannot replan. It doesn't matter if you have like thousands of computational power. At the end, you need to handle dynamic obstacles properly, right? It's not a matter of replanning fast enough. we need to take them into account into our planning, right? Because you see, this is very inconvenient. The robot just stops. It doesn't find a path, so it has to stop for safety. And, well, you will be surprised, but this is still probably the most used planning technique, even today. If the environment is static, this should work fine, right? There's no problem here. But I think if we really want to deploy robots in social environments, like indoors and outdoors, we really need to take into account these peculiarities. Okay, so for that, as I said, we need motion prediction. The first step is intentionality. I'm just skipping a lot of content inside, but I think the takeaway part is this one, right? So what is these lines? The blue dotted line is what happens when you do prediction without inferring what is the intentionality of your environment. So that simply you calculate a state and you just propagate this over time, right? Let's say that you have first order estimation, like your velocity, and you keep propagating this. So it's good, if you see on the x-axis, this is time. For 1 second, the accuracy of predictions that you will get is fine. But as the time horizon grows on this prediction, this really degrades very quickly, right? So in fact, after even 3 seconds or 4 seconds, we don't really have like good prediction. So this will be the result of tracking. This is not good enough. On the other side, what happens when we include like goals, right? Goals or intentions, I think that's something that you might have discussed in other topics, right, in machine learning, right? So this really changes some of the distribution, right? So knowing what you want to do is not the same as just predicting your state or propagating your state. So the difference is really huge. You see here the 2 lines. This is just a variant, each of them. But both of them are including intentionality, right? So we are just inferring which is this goal that we have on the environment, and after several seconds, we still have like a high accuracy of prediction, right? So, well, this, if you want to know more details, there's a publication on this, but I think this is the important point, right? So goals and intentions, this really makes the difference. The second part on motion prediction, and again, this is like going faster and just explaining things, is once we know these goals, how can we feel the trajectories? That is like at each time step, how can we know which is the state of these agents are going to do over time, right? So for generating these trajectories, we are going to use like a model, and I will discuss later, right, how good or how bad this is, but we are just going to use a model that was used for neuroscientists, just to predict like evacuation scenarios and other things, which is called the social force model. So now imagine any scene. First, with the previous algorithm, with the intentionality prediction, we know which of these 2 destinations the agent is going to go to, right? So then we decide after running this algorithm which one is the winner, and after we know that, basically we are going to treat like every pedestrian as a 2-dimensional point, right? And it's called force model because the trajectories are just going to be described by these forces generating these 2 objectives, right? From one side, the agent wants to achieve a goal. This is the destination that we have inferred. And from the second, the second kind of interactions come from other agents, right? So there are other agents, you don't want to collide with them, so basically they generate what we call a virtual force. It's not just person-to-person interaction, but also we have interactions with obstacles, you don't want to collide with them. And then there's a third one, which is the one that we studied in particular, right? So the interaction with robots. So we have a robot, this is not exactly a person, so the force, the virtual force that is going to generate, it's going to be different, and this is going to increase the accuracy of our prediction. So we just apply superposition, sum up all the forces, and the resultant force will generate our trajectory, right? We do that over several time steps, and with this we generate a trajectory. So let's see this in action, right? In this case, we have here an agent. All these circles, let's say that this is the error propagation, right? Because this is still uncertain. We have agents, we don't know what they are going to do, but at least, well, if we just do error propagation of this system, we'll get something like this. So the agent initially stays here and tries to get to this destination, right? So it just follows the force-based approach as we have explained. Now what happens when we add another agent here? Right, so it's very subtle, but there's a interaction between them. So these predictions, all of them are related. And this is thanks to these virtual forces. So in this case, the initial agent changes slightly its trajectory, and then the red agent, green, sorry, definitely it has to adapt its plan to whatever the other agent is doing, right? So this is kind of dance between agents, and well, basically this model gives us like this idea of how approximately the system is going to evolve over time. Okay, so this just applied into a real environment. We were there in old campus in Barcelona, traveling with our robot. You see this humanoid thing, and then we will basically matching the accuracy versus what actually the pedestrians did, right? So in this case, these green again, cylinders are just the predictions. They are not super accurate, but they adapt well in time. And then we have like some time horizon of what they are going to be doing, right? So this was just part of the motion prediction. Now the interesting part is what do we do with this, right? We are interested in robot navigation, so how can we use this? Well, the initial takeoff is that just using this model actually leads to local minima, so the robot gets trapped, and this was a solution that we found just to overcome this. So we have a set of predictions. We detect and track all agents, and then our robot has to decide which is the best action to do, or best path, right? And here you see the overall scheme of this approach. So we have a map, we have a global planner, and then basically the solution is thought. You see these red lines here, red lines here, right? These are the potential paths that the robot can take. And for each of them, and this was actually the new part, we were able to know exactly how much the predictions were deviating from their original goal. So it's not just having a good prediction. Prediction is end-to-end with planning. If we have a robot moving, prediction changes. And again, this is a very hard problem, because even though you had the best prediction available, 100%, which is not realistic, but even if you had, this will change the time that you have like other agents doing some other actions, right? So there's always a balance. And well, let me show you now some videos of what is this result. I will also talk about the limitations. So here you see the green tornadoes. These are predictions. I'm plotting here multiple of them. For each prediction, no, let's say that for each blue trajectory, all these blue things moving from the robot, there's a prediction, right? All of them kind of stay the same, but there's small difference inside the green tornadoes. So we need to find which is the path that actually optimizes, like the objective function. So we have several of them. We are just here using sampling. And still, well, you see that, yes, it does something. It doesn't really move like super fast. Sometimes it feels so. Well, first one is because this robot was not really fast. The second one is because we are calculating at each time step the full solution, right? And this was very costly. That was very expensive. So let's say that just running this inference of intentions, prediction of the trajectories, and then sampling all these robot trajectories was like really expensive. So So basically with this concern on real-time application, we came to the next step or next research line. This, as I said, I will be discussing some techniques widely used in machine learning, right, that we are using here for planning. And the main objective here is to make this more efficient. So it doesn't matter if you have the perfect plan, if you calculate it 10 seconds or 1 minute later, right? The moment just has gone, and maybe your robot has crashed, or your car has crashed with something, or your flying thing, well, didn't do well. So this is even as important. Optimality is important, but the efficiency and the real-time execution of these algorithms, I think it's equally important. So what are we proposing here? So rather than just calculating the whole trajectory all the time, right, which is very computationally intense, with this approach we were proposing to select among some policies, right, and I'm going to describe later what these policies are. We are just going to select which ones to execute. So what is the advantage of this? Let's say that we have now like hierarchical planning, where on the height level we select which policy to execute, and once we have selected, the policy can run at a much higher frequency, right? So policy is just taking states as inputs, and it's outputting like some action. This can go very fast, like in this setting we were like at 50 Hertz, which is, I think, higher than some of our inputs, but still it was very reactive. Inputs, I mean sensor inputs. So, well, if you're interested, we are using LiDAR sensors, and I think this one was going at 20 Hertz. But still, this was very reactive, so we had like a action like almost instantly, and then this selection of policies can be a little slower. It's not that slow, right? We can prevent many things, but basically just by separating the problem, well, things start working very well. So let me talk now about the policies. Again, these policies were just the first initial proposals, but here you can also be learning policies. I think the important part here is that we cannot really have a policy for everything, right? So that's a little the price that we are paying. So imagine you have infinite perfect data. I will talk later about this, but and then you train your policy. Yes, fine, but I think that's theoretically correct, but in practice doesn't work so well. So you still, at least in this approach, you need like some policies. First one is just go solo. Go solo is what we said, you have a goal, you have some environment, and we were applying this model from neuroscience, the virtual forces, just to do a trajectory. So from the point of view of optimization, this is just a greedy approach. You always try to get closer to your goal, right? So sometimes this can be good, but others, this is not really best option, right? So it's very greedy. The second one, this is common sense, right? So you stop. Whatever your state is, you try to stop. Okay, not surprising, yeah. The third one is, but we'll see how this combines, which I think that's the beauty of it. And then the third one is just follow. Let's say that we are in very cluttered environments, so this initially handcrafted policy is just trying to follow like some agent there. So that means that there's some velocity and some position of this agent, and it's just following this. So this somehow alleviates the problem of calculating what is the actions that you should be taking. Just copy whatever they are doing. Okay, and now let me talk a little about what are the cost functions here. So on one side we have what we have called progress, but this is logical. The planning problem, as I said at the beginning, is moving from point A to point B, right? So this is just a measure of how close you are from getting to point B, right? So if you don't get there, basically you will not get, well, your cost will be high. And the second one, and I think that's where we have some balance, because this objective actually it's opposed to the progress or achieving a goal, is blame. Blame is a short name just to express this inconvenience to other agents. Extreme blame would be you hit someone, right? That's not ideal. Still, if you are very close, this also creates like some inconveniences, and that's why we are measuring this. So why I'm saying that these are opposed? Because if we just consider progress as it is, we will always have like a greedy approach where you just get, you always try to get straight to your goal. So you can imagine that means that you just go through a bunch of people, a bunch of walls, whatever, the robot is just going straight. On the other side, blame, if you want to reduce blame, it's simply like a robot that never reaches the destination. It's always afraid of moving close to people, right? Because this creates small amount of blame, but still on the optimization, from the optimization point of view, that's more than just doing like an infinite round. So these two things have to be like opposite, but we need to consider both of them. Okay, and how does the algorithm works? So we have like some states for each agent, in this case x, right? For each agent, we have a position, we have a velocity, and as I said at the beginning, we need to infer goals, right? So it's a 6-dimensional vector. We have n agents, that can be one agent, 10 agents, that depends on the, conditions. And then just to calculate what is the expected cost, well, we just run sampling. So why sampling or on which variables? So basically, we are not sure which is the state variables for each agent. So that means that there's a lot of uncertainty on the goal estimation, there's uncertainty on the velocity, and well, on the position, not so much, but still, that's something. So basically, these are just random variables, and we cannot say that we can observe them directly. So this will always be like our problem, or at the same time, this is the advantage. So if you treat them as random variables, you can think that, okay, so minor perturbations on these initial conditions can lead to some trajectories or others, right? So we just approximate the expectation of this cost, and then we just choose here what is the policy. In this case, psi, what is the policy that gives like better results? And remember, here we are not doing, this is not policy gradient or, no, we are just choosing among a limited set of policies, right? So we run the algorithm for, different samples, choosing different policies, and then we choose which one is the one giving like best cost. Okay, so let me show you now some of the emergent behavior that happens after doing this. This is the problem that I talked about initially, so this is what we call local minima. Just choose always go solo, and this is what is going to happen. You have a robot that tries to make progress, and when you find a pedestrian or, let's say, a local minima condition that you cannot overcome, the robot does very stupid things, and I would say that even dangerous, right? So here starts like spinning on its side, and I think here it's almost crashing with the wall. So no. And this is the same, we try to recreate the same conditions, right? Just combining what happens when we can choose between just go solo and stop. And this is a very common thing, but still we need to express this algorithmically. So you see, well, it's navigating, decides to stop because it sees someone, and the best thing is not to crash against the wall, it's just to stop. Okay, and the same thing happens again. So more of these examples is, we are also here in this clutter corridor. Well, the corridor problem has been studied a long time, but still it's hard. And I think it's not hard because planning is complicated. Here it's because perception, and especially the estimation of all these agent states, is complicated. So in this case, it's just choosing among these two persons moving in front of it, right? And it's just changing the follow target. Here it's the same thing. So we have an agent that we don't know what it's doing, right? Walking backwards, that's very strange. So let's stop. And here it's the same, right? So these people wandering, it's not a good idea just to get very close to them. Okay, so yeah, and here we have the same kind of environment. We have a clutter, the robot is just trying to move, and just by this simple selection of policies, the emergent behavior that the robot can do is like quite surprising, right? This is much more efficient than the approach that I was talking about. On that approach, yes, you look for optimality. Probably you can find like optimal paths, but it's very expensive. So sometimes the price for that is that when you want to execute that, it's already too late. So this was like very, very fast, and we got very good results. Not perfect, so let me show you now some of the limitations. So the limitations are not really on the approach by itself, it's on the nature of this problem, right? So we have a limited set of samples. That means that, yes, on the limit, with infinite samples, we have an unbiased estimation of our cost function, but in reality, with a machine inside the robot, well, we don't have like infinite samples. We just have some of them. And this was an experiment that we knew that the robot might fail, right? So it's basically, on this configuration, the robot, most of the plans, that means each of the samples that we have on the problem, are giving like a positive or small cost, saying that yes, it can go through this wall of people, just moving or cruising in front of it, because although the potential dangerous is high, on this simulation, all these samples predicted like low cost, right? So it's only, let's say that these misses, small misses, like coming close to a person, it's not that bad, but actually colliding have like a high cost. So basically, there were just some of the initial configurations that combined resulted in this kind of problem. So what does this mean? This means that sampling is fine, but we are actually interested in height influential configurations. And by height influential means this. We are looking with our limited sample budget, we want to find these configurations that might end in potentially dangerous outcomes, right? So this is just an example. Okay, so a little of math, not much in this. I think this is the only slide where or the previous one. So this is standard way of calculating your expected cost, approximated with samples. Let's forget about that for this problem. In others, yes, this is the way to go. But instead of that, what we are proposing is a search, right? So we don't have here, infinite budget of samples, but we are going to transform this estimation of the expectation into just a search, right? And what is the idea behind? So these height influential costs have high cost, right? If we don't include here the probability, that will just look for kamikaze-like outcomes from the pedestrian, so that's not really close to reality. We don't really want that, but somehow just leveraging this cost by our initial distribution of states. In this case, P of X is the state that we are observing from other agents, right? So the position, velocity, and especially the goal, right? Just by having this distribution, this acts like some sort of regularizer, and still we can find like these height influential costs that are potentially dangerous with drastically reduced amount of samples that we need. Well, in this case now, samples are just iterations into our optimization method, and then we need like several initial conditions, right, just to change, well, initial seeds, right, just to make the optimization good. But basically, yes, we are just changing the estimation problem with an optimization problem. So influential, well, that's this combination, right? So it has to be likely. That means that it has to be inside this estimation of our state variables. And then we are looking for height cost, right? And this height cost, this is very clear. So the higher means that probably closer, even a collision. So we want to avoid that. Okay, now let's take a look of how this problem looks like. Each of these agents has a trajectory, right? These are the red lines. And remember that here what we are doing is we have a small, and for now it's a small, set of policies. We are just evaluating them just by being, or let's say, calculating this adversarial outcome of these height influential outcomes, right, just by changing slightly the trajectory. So in this case, you see these lines. These are actually the gradients. That means that the agent speeds up a little or changes a little to the right? And in this case, agent 0 will actually collide with the robot, while if you go a little to the left, it will avoid the robot there, right? So we are just doing that, slightly moving over the gradients on all these agents that we are perceiving and making them the resultant cost be higher. That's kind of trying to face the robot. And the robot just has to choose, so which is the best policy to execute. Okay, this is better shown in an example. On top you see the previous failure kind of thing, just with non-informed sampling. And on the bottom, you see the solution, right, of just doing the optimization over this cost function. So with the same number of samples, same computational budget, these were fair conditions. On the first example, it was not possible to always, you know, create like a safe navigation or safe navigation behavior, but on the bottom, all the time, we found like a solution that was more convenient. So, yeah, this is also like not a repeatable example. With this repeatable example, we got, you know, like, well, was like quantitative evaluation, but this was just, okay, so let's get like some taste of how the algorithm is behaving, and we would just put people there, and we were asking them to navigate, like, naturally, maybe not much, but they were like making the robot task a little more complicated, right? So they were just there, and still, I think the robot didn't collide with anyone, even on hard conditions, like hardly predicted conditions. Still, the robot was doing a very good job, and this is not just because prediction was the best. It's because it was very efficient. We can, oh yes, this is unexpected also thing, so someone starts running and the robot is still able to predict this. With the previous approach, there was no chance that we could react on time for these kind of very dynamic things. Okay, and now let's move on a little. So I guess I have convinced that optimization is kind of very powerful. Maybe you are already, so because optimization, you are using this in many, many other algorithms. But let's express this problem a little more formally, right? And this is what we call backpropagation multi-policy decision making. And that's why on the title I mentioned like planning network. So what is exactly that? Well, this is not something new. This is something that has been here for a long time, but still, we could reformulate the problem, or not reformulate the problem, but adapt it just to make use of this very powerful technique, which is backpropagation. So the forward paths are very clear. You just have a system, you keep propagating, right? In this case, we are just calling these transition blocks, right? So you have a bunch of states. Remember, each of them is position, velocity, and goal. And well, the robot is also included into these transitions. And then you get like next state. You do this several times and you have trajectories, right? So this is basically kind of a network. We are also calculating, which is the cost. In this case, L. So remember, cost was including our progress to the goal and blame that we were doing. So these opposed things, which in principle we should have like opposing gradients, but in reality you can really find like highly or adversarial trajectories just by doing this. And then you do this several times. You calculate all these values on the forward pass, and on the backward pass we can calculate the gradients. Right, so at the end we're interested in the initial conditions, this x0, well, right, we want to perturb them just to find these highly influential things, highly influential configurations. Before, well, we did the optimization not so principled, but I think with this, what we improve is on how we were calculating gradients, so this is much more efficient. This is actually the main difference with respect to using any other or standard optimization method. So what do we need for this? Well, we just need a differentiable operator, right? It gives some input, it outputs state, but it just has to be differentiable. We don't care if it's linear, nonlinear, highly nonlinear, whatever, but we need like differentiability. Here, cost function also, we are breaking this down, so at each layer we have like also a cost function. And well, once we have this, it's very easy, right? You can use standard techniques just to backpropagate things and get gradients like very efficiently. The difference here is that in this network, we don't have like parameters at each layer. Imagine that you are just fixing these blocks. And this is actually a debate for another topic, which will be, okay, so now you want to do these transition blocks better, right? So what do? You use exactly the same network with, let's say, observed data, and then you will be optimizing over these parameters in the training state, right? On this part, this is more related to the inference, right? So we want to execute this in real time. We want to know what is the problem of executing this policy, and that's why we need to calculate this gradient so fast. As I said, this is not new, so basically all this is dynamic programming, right? So there has been many things on the literature, like linear quadratic regulators, DDP, etc., right? And again, this can also be adapted to learning, but as it is now in this problem that I'm explaining today and that I have published some results, we were using just for planning. Okay, so yeah, some evaluations of what is the difference here. Basically on the first graphic, you see this blue line. You see that this behaves, or the complexity of this with the number of agents, it's not really good, right? It's fine for 3 agents, 4 agents, but the moment that you have 8 agents, this actually goes like beyond our calculation capabilities. While the backpropagation technique in green, right, still it's affected. There's some complexity, of course. We cannot do a constant, well, that would be great if you think on that, like a constant complexity optimization method here, that will be great, but it's hard. As it is now, it's there, right, but it behaves much better. So this is just thanks to the backpropagation way of calculating gradients. And well, in red, this is just random, random sampling, which, okay, it's fine, but we might lose, and this is the important thing, we might lose these height influential outcomes, which can be very dangerous. The second graphic here on the top is basically we were comparing like what is the blame, right, that we do while traveling, and the time stop. So it's also, why is this graphic? Because it might be like tricky or cheating, just stopping all the time, right? So you can find like this is a good strategy and you can exploit that a lot, but in fact this is not so efficient, right, from the time that you spend traveling and doing the same task. So we were leveraging these two things, although they were not enforced directly into our cost function. Our cost function just includes blame and progress to the goal. So again, in red, we see what happens when we have like, using backpropagation here, there are like 2 time budgets. One is 0.3 seconds of calculating and the other is 1 second. We improve a little, but the great thing is that it really improves with respect to our previous way of calculating just the gradient, right, which was just stochastic gradient ascent, so, which is the blue line here. Okay, so basically, the closer you are to 0, 0, the better. Let's take, because this thing is very nice if you take evaluations, but I think it's better seen a demonstration, right? So here is what's happening when we have, in this case, we don't have 3 policies. Thanks to the backpropagation improvement, here we are executing 10 policies, if I remember. This is a combination of several speeds and some different goals for the robot, right? And at the end, in this environment was actually a little more challenging because now people, volunteers, were there like really doing like some inconvenience. What happens when we have like new kind of agents, right? So in this case, we have this fast agent. We didn't train for bicycles, but well, it works. So still we have like this feeling of safety. We are not really crashing. And well, this is just because of the efficiency. So this is a great thing, backpropagating planning things and just using optimization. Now there's a next step that we did, and this is actually, I guess most of you have already this in your mind. So okay, so you have a set of policies. That's very strange, right? So how can you really handcraft like policies even though you are changing these parameters of speed? That's probably not the best thing to do. So, well, we can argue if you can learn them, that's totally possible. But then what we propose is instead of having reduced set of policies, we're just going to propose a continuous set of these policies that depend on some parameters, right? And in this case, the parameters were just goal that the robot will be heading and some speed, right? So you can imagine the profile of speed, how fast it goes. So is it possible just to have with this still infinite number of policies but reduced set from all the things that the robot could do? Can we still have like a better robot navigation with respect to just have like particular policies? Right, so again, we use the same architecture, right? This I think, was really a difference between before and after. So we use the same architecture, and here the difference is that now we have a policy on the robot that is just affecting all the robot transition, right? So it's this green dot, right? The network is the same, you just have several layers of transition functions, right? Your agents evolve with whatever they want to do or how well you are calculating them. And then the problem becomes a bilevel optimization. So from one side, we want to test all these adversarial initial conditions. So we want to find the highly influential outcomes, that is crashes and these kind of things. This will be like one way of running the network. And the second one is, okay, so forward propagation requires like a fixed policy, right? So on the second run, we'll be doing exactly the same thing, but just optimizing for the policy parameters, right? And in this case, we are not learning here. We could be doing, but I think there we need really like to label data correctly, and this is a little challenge, but still this is just for planning, and with this continuous number of parameters on the policy, we will do a second run, right? So you forward propagate everything, you try to find like what is the best thing that the robot could be doing in this very adversarial thing, and there's basically a game, right? So the robot tries to find the best solution, and then the agents perturb this to make it highly influential. You do this several times until you find like some equilibrium. This is also, I believe, used in other areas, right? So, okay, let's now take a look at the results. It's green dots. Here we were comparing again the blame with respect to the time stop. And as I said, the best one is, it's the same graphic as I showed before, but I simply increase the scale. So before, I think one, well, here on the y-axis, one was almost at the bottom. That means that we were comparing methods that were stopping a lot. And here, all of them are very good. So we are just doing like random, selecting random policies from this set of parameters, right? So this doesn't work well. This is the red circle. Oh, this is not working. Red circle. The previous approach, these handcrafted policies, and here in green, this is our approach, right? So that's what happens when you do this bilevel optimization. You find or you search for highly influential outcomes, and at the same time you are optimizing your robot policy. Okay, so this is an example. This was the previous one with discrete set of policies, and this is exactly the same example that is happening with continuous policies. I'm going to play it again. So you will see the difference because on the discrete set you see like a harder transition. Basically there's like a switch between a policy going on some given velocity and then a lower velocity. And then the continuous one, you simply see that things go slowly. So this was like hard, almost hard, and this goes very slowly. And this is just the continuous parameterized policy. And here we did the same thing again, right? So they were just being like, we tried to make this like very adversarial, and the road was still able to navigate. Here, remember that safety is very important, right? We don't want to crash with people. Although you might have like in expectation good results, it's actually the other side. We should be looking for almost zero safety issues, right? So averages here I think can be dangerous, 99.9%. It's okay, it's very impressive, but that means that 1 out of 1,000 you are going to be hitting someone. In robotics, let's try to avoid that. Try to avoid that. It's still not happening. Okay. Oh, yeah. So now I've talked about some of the, well, research topics that I've been working on during the past years. But since this is a machine learning summer school and open day, right, I think most of you are interested in this area. So let's just do a little discussion on what is happening, or what is the point of view, let's say, from robotics, right, with respect to other machine learning. So, well, I repeated this many times, but I think this is very important. Mistakes can lead to potentially catastrophic results. So I said that having a recall of 99% is great on some data sets, but here that means that you will be doing something bad, right? So we cannot really measure things on the same way as pattern recognition community is doing. So yes, we must ensure safety, right? It doesn't matter if it's from data-based methods, right? So you learn them or you obtain them from a model. We must ensure safety, and that's kind of an issue. So this is a particularity, but I think it's an opportunity, right? So think of ways of how to ensure this kind of thing, not just, let's say, my guess is that using averages works well, but here we should be using like some sort of different utility function. We start doing some of the things, but yeah, there's definitely a lot of research opportunities there. And then the second one is uncertainty, right? So how much trust do we put in our prediction algorithms? That's basically saying, okay, so you have your train algorithm based on whatever. How much trust you should be putting there? And I think that's an important question. It's not just, you know, measuring how well you have done overall, but we need to measure somehow the uncertainty here. So for robotics, this is something that we should be looking at. And if you're working on prediction problems or machine learning problems, I think that the robotics community needs this kind of measure, right? How much trust do we put into your predictions? Okay, so second point, I don't think this is good or bad, right? So all these data-driven approaches require less knowledge on the problem. It's good, it's bad, well, I don't know. It's just a fact, right? You just sometimes run the algorithm. But the problem then becomes obtaining this high quality data, right? And in our case, how can you label this data? What was a bad outcome? So a collision is very clear, but a close-valve collision, it's not so clear, right? So how to label that? I think this creates like a difference on how your algorithms are gonna be behaving, right, after running your algorithm. So it's a tricky part, but I think, yeah, that's something to think about. The second one is, okay, most of these algorithms that you might be using in machine learning will require a lot of data, right? So how can we obtain this data? Running real-life robot executions in the real world, that can be very expensive, not just from the point of view of, well, basically, yes, it's time, a lot of time that you need to be there running your robot. So that's not ideal. Still, we have simulations, right? And I think that's good just to bootstrap your model, but then how well these simulations transfer, right? So there's still a lot of ongoing research, how to do all this transfer like nicely and still, you know, keep improving your model given the gap that exists between simulations, which are good, very good, and reality, which is not simulation. And then, well, this is more open question. So still, we have seen like a tremendous success in other communities, right, on deep learning approaches, but not really in robotics. I mean, there's a lot of very cool things going on, and I think the progress is there being done, but still, we haven't seen like this explosion of all of a sudden the paradigm just changes from one year to the other. So why is that? I think it's basically with this talk you will get an idea. So the evaluation is essentially different. You cannot really take a data set and say, yes, 99%, this is good. Now, you actually care about the 0.1%, and this is very tricky, very tedious, and, well, open. What's up? This is last slide. And And then, yeah, so real world, right? Real world is also very challenging. We just have our predictions based on some data, but sometimes real world is, well, challenging. The elephant in the room and these kind of unexpected events. And well, that's it. Thanks for your attention. Maybe I can take some questions. 1 or 2. Oh, thank you.